Assistant Professor at the Department of Mathematics, Sacred Heart College, Chalakudi. Today, on day 7 of NEPM 2020, we will see how to define a topology on an arbitrary set X, how to define a lattice, and also how to identify this lattice and set of all topologies on a set X, the concepts together. A warm welcome to you all. Let's begin our session. So you saw about a video which said something about a coffee cup, a donut, and a cow. So from this video which you saw, maybe we have two inferences. And in the first inference, we have a question which says, what should be that coffee cup be made of or the cow be made of so that it can be deformed? The coffee cup can be deformed into a donut as well as the cow, the normal cow is deformed into a spherical cow. The second inference is how to mathematically analyze this deformation. Coffee cup to donut and vice versa. Similarly, a normal cow to a spherical cow and vice versa. So, as we are studying mathematics, indeed we have to bring all this into a mathematical term. So, let's compare how we can bring it into a mathematical term with a common man's knowledge. So, in layman's terms, the area which we are going to deal with can be called squishy rubber sheet geometry, because we had the first inference question which asked us what type of material this coffee cup as well as the cow should be made of. So we are thinking about the material to be squishy rubber sheet because it can be deformed from one into another. Okay, the same thing is mathematically called as an area of topology. Okay, and when a layman or a common man says an object X, you can call this X as the coffee cup, okay, and Y as the donut, so that we can understand it better. So an object, the coffee cup, is deformed into the object donut through the process of twisting, shrinking, and stretching. Okay. The same idea is mathematically called as the follows. The object is called in topology to be a topological space. So here the coffee cup is a topological space and the donut is also a topological space. Okay. So this coffee cup is going to change into donut. Here we had some kind of deformations. So the deformation here is called as a map. Okay. So a topological space X is identified to another topological space Y using a map. And this map has a name in topology and the name is homeomorphism. And just to give an intro to what is homeomorphism, it is nothing but a 1 1 onto, that is a bijection, which is bicontinuous. You don't bother about the terms which are coming here, which are new to you, because a topological space is new to you, a homeomorphism is new to you, and also bicontinuous is new to you. These terms, as we study topology, we'll come to know them better. Okay. And the third thing for a common man is both objects can be transformed into one another. Okay. And For a mathematician or a topologist, a person who is studying topology is called a topologist. Both the topological spaces are called homeomorphic or topologically equivalent. So to conclude, we can say about this area in mathematics to be a mathematical study of the properties which are preserved through deformations, twistings and stretchings of objects. As we were comparing in the table before, you had a disclaimer sitting here. This disclaimer is saying that neither tearing nor gluing is allowed. So we can neither give a tear nor glue something together when we are trying to deform the object. So to have an easiness, you can think about the material to be the clay which we play when we were children. Okay, so this clay can be deformed from one object to another, and always remember the disclaimer in topology which says neither tearing nor gluing is allowed. So to define a topology as we move on, a basic analogy of a set. A set is a collection of well-defined and distinct objects considered as an object in its own right. That means they should be well-defined. Okay. As an example, I am giving you a set X. The set is denoted as X, capital X, which is equal to the set a triangle, a smiling face, and a five pointed star. Okay, this is an example of a set. Now, a set Y is a subset of a set X if every element in Y is an element in X, and we denote it as Y subset of X. This is the symbol for subset of X. So as an example, we had the same set X which has the triangle, the smiling face and the five-pointed star, and a set Y1 which is equal to the smiling face and a heart, and set Y2 to be the set, the smiling face and a five-pointed star. Okay, and from this you can conclude that y2 is a subset of x, but y1 is not a subset of x since the heart doesn't belong to x. Now a power set of a set x is the set of all subsets of x, and it is denoted as script p of x. So as an example, we have the same set x and the power set of x is equal to the set, null set, which is denoted by phi, comma, the singleton sets of these elements, and the two elemented sets, subsets of the set X, and then the total set X. So this is the power set of X denoted as script P of X. So our first aim is, given a set X, how to make the set a topological space. Okay. For that, we need a subset tau. Tau is a Greek alphabet, T-A-U. It is pronounced as tau. A subset tau of the power set of x, that is tau subset of the script P of x. We need such a subfamily. And then this particular tau we are saying or talking about should satisfy three conditions. Okay, so for X to be a topological space, what do we need? We need a subset tau of the power set of X which satisfies three conditions. So we are going to see what are those three conditions this tau should satisfy. The three conditions tau subset of the power set of X should satisfy are, in this tau, the null set phi and the full set X should be present. That is the first condition. The second condition says that if two elements or two sets belong to tau, their intersection should also belong to tau. And this will lead to finite intersection of elements in tau to belong to tau by induction. Okay. The third condition is, suppose if AI belongs to tau for every I belongs to an indexing set I. So this indexing set can be finite, it can be denumerable, or it can be infinite, or whatever. Okay. So you can call it as an arbitrary number of sets that is in tau. Their union, the union of the arbitrary union of those sets should be in tau. So we can say that arbitrary union of elements in tau belongs to tau. This condition is reduced like that. Okay. So if the tau we are talking about satisfies these three conditions, we call tau as a topology on X. Okay. And the ordered pair X together with this tau is called as a topological space. So what did we do now? We had a set with us and we introduced a tau which satisfies three conditions, and this tau is a subset of the power set of X. And if it satisfies those three conditions, tau is called a topology on X, and X together with this tau as an ordered pair is called a topological space. So let's see some examples related to this. Given an arbitrary set X, the smallest topology we can associate with this set is, you can guess, because we definitely need the null set phi and the total set X to be inside the topology. So the set, the null set phi together with the together with the total set X is a topology on X. And that topology is called indiscrete topology on X. And I am, for our easiness, I am calling this tau suffix indiscrete in order to differentiate. Tau indiscrete is equal to set phi and X. Okay. And X together with this topology tau indiscrete is called the indiscrete topological space. Okay. Since we said about the smallest topology we can associate with an arbitrary set X, we can also think about the largest topology we can associate with an arbitrary set X. That is nothing but the set of all subsets of X, which is the power set of X. And it is called the discrete topology on X. And it is denoted as tau suffix discrete. Tau discrete is equal to this power set of X. And the ordered pair X along with this discrete topology is called as the discrete topological space. So from this we definitely know that every arbitrary set will have an indiscrete topology as well as a discrete topology. So that is the next remark. Every set X will have indiscrete topology and discrete topology on it. So example 3, suppose the set X is equal to set singleton set A. Okay. So we can say that tau indiscrete is equal to the set null set phi comma X. X means the singleton set A, right? But that is nothing but tau discrete here. Okay, so what we conclude here is whenever a set is a singleton set, we only have one possible topology on it because the indiscrete topology and the discrete topology coincides here. Okay, now the next example is, suppose if X is equal to set A comma B. So definitely this X has the discrete and indiscrete topologies associated with it. And also two other possibilities are there. The first possibility I call it tau1. which is equal to the set null set phi, the singleton set A, then X, and tot2 is equal to the set null set phi, singleton set B, and the total set X. So in total, for a 2-element set, there are 1, 2, 3, 4 possible topologies on that X. So next is also an example which you have to work on. This is the first question you have to work on. Suppose if X is equal to the set A, B, C, write all the topologies possible on this set and hence find the total number of topologies on X. This is your first task. So, see you in the next video. Till then, bye.